Okay, in this presentation, we are going to go through Angular PVA using the graphing technique. So let's do Angular position, velocity, and acceleration. And the activity that I thought we would go ahead and describe would be elbow flexion. Elbow flexion, extension. So real simple movement where we're going to take the elbow. Let me draw it. I'll draw it big this first time and then I'll do PVA. So this would be the hand down here. Well, maybe too many fingers. And this would be the elbow. Oh, you couldn't see my fingers. Okay. And we'd have the bicep here and tricep. Okay, things like that. What we're going to do is quantify the angular kinematics of the elbow while the hand goes up and then back down as we go through flexion and then back through extension. So remember, the first thing we need to do is settle on what our reference frame is and what our we're 0 degrees. And remember, we have anatomical position is set to 0, or we have word on the street where anatomical position would be 180 degrees. So in essence, what we've got to decide is when the elbow is in this position here, again, this is the hand down here, is this 0 degrees or is this 180 degrees? They're obviously related to each other. And the way that we actually envision the anatomical position 0 is we actually extend the humerus outwards, and then we take the angle between that dotted line and where the forearm is. Clearly, this entire angle is 180 degrees. But when we do that setup, we have anatomical position, in this case, is 0 degrees. And then as we move through flexion, we measure that angle right there. Now, the other angle, word on the street angle, would be this angle right here. And those two angles will add up to 180 degrees. So this may be 120 degrees, this may be 60 degrees, but we would say 60 degrees of flexion, or we would say the elbow angle is at 120 degrees. So for our purposes of this presentation, I'm actually going to go ahead and select anatomical position as 0 degrees. You actually see that will make more sense as we go through different angular parameters and as we start moving into angular kinetics. All right, so let's go ahead and use that reference frame. When you're in anatomical position, the elbow will be in 0 degrees, and then as we start going through flexion, that angle increases. So now we're going to identify our graphs for angular PVA, and I'm going to do 3 plots, and I'm going to do angular position this way. This is theta, and this is time on this axis, and then right below that I will do angular velocity. And that's omega, and these are degrees per second. We could also use radians per second, and we'll use degrees up here as well, just to be consistent. And notice I've left an area for positive, 0, and negative angular velocities. And then right below that plot, we always stack these plots up on top of each other so we can see how the time aligns and what's happening. Then we finally have angular acceleration. And that's alpha. and we'll use degrees per second squared for our units. And again, positive, 0, negative regions for angular acceleration. All right, so now we're going to think about elbow flexion, pause, and then elbow extension. Knowing that anatomical position is 0 at the beginning, we're going to be down in this region with a fully extended elbow. And now we go from this region up to a fully flexed position. I'm going to put a dot right here. All right, fully flexed. All right, and then we're going to pause at that for just a bit. And then we're going to go through extension and we're going to come back to 0. So now I just need to, in essence, connect these dots. And I'm going to go ahead and connect them using a curved line. But in essence, we want to avoid straight lines, and it makes the math a little better when we don't. But it's also in human movement, we hardly ever go from nothing to some constant velocity. So I'm going to draw sort of a shape that looks curved and like an S, big extended S. Okay. So what's going on here? Well, we're going through flexion. Okay, and I can even put flexion here. We're going from 0 degrees to maybe we go all the way up to 120 degrees of flexion. And that's fully flexed. We don't go all the way up to 180 unless we break our arm. All right, and so we have all these angular positions here. Now we're in a fully flexed position. Then we come back down here, and again, I'm gonna draw that sort of a S shape here. It's a little subtle, but it's there. All right, so now we have our angular position. So we have flexion, and then we have extension. So flexion phase up until here, and then extension until the end. Okay, and then just here we're in a static position of no movement. All right, so now what I want to do for purposes of getting velocity is I want to drop these points down to the next plot. So I'm going to go all the way down to here. Go all the way down to here. I'm going to identify the different phases of movement by those discrete events. So this is still flexion. This is still extension phase. So flexion, extension. All right, so same phase, same phase. And then no movement in between here. So now we want to start thinking about, and no movement after we're done too. Let's start thinking about velocity. Well, what's velocity? Rate of change of angular position. And if you remember, we have on this plot, if we look at the slope of the line, the slope is rise over run, and the slope is change in position over change in time, which is exactly our formula for angular velocity. So if we look at the slope of this line anywhere here, we know everything we need to know about angular velocity. Well, let's identify the direction of angular velocity to begin with. And let's look at the direction of anywhere of the slope anywhere in here in this region. And if we look at even little itty bitty times in here, I could make these dashes if I want. I know you can't see them, but if I make dashes here and look at the slopes in little sections of this curve, we would notice that all the slopes are positive. They're all positive anywhere in here. And so I'm going to put a big plus sign, or well, I'll put a plus sign in here. And that's one of our first clues of what's going on with angular velocity. Angular velocity will be positive when we go through flexion, when we use the anatomical position is set to 0 degrees. Anywhere where angular velocity is positive, we'll be going through flexion. Okay? Extension, let's do the same thing here. If I look at any individual little time period in here, all these slopes, any slope in here is going to be negative. That's our other clue of what's going on using our angular velocity parameter. Anytime angular velocity is negative, that indicates we're going through elbow extension. When we're using anatomical position is set to 0 degrees and flexion angles are increasing. So now I know positive angular velocity is flexion. I know negative velocities are extension. Well, what about this region right here? Well, remember, anytime there's no change in angular position, it doesn't matter what the time period is going to be, angular velocity is 0. So anytime we see a straight line, we know velocity is 0. So I'm going to try to make that section here. Okay, 0 velocity. And if I hold the position afterwards and before, I know velocities are 0 in the beginning and 0 in the end. Okay. All right, so now I need to draw in something here. I have some positive velocities, I have some negative velocities. And maybe I didn't do too good of a job here, but what I'm actually trying to draw is a shape of a curve that these slopes are increasing until some point, and then they start to decrease at some point, right? And when we see this change in curvature of this line, we call that an inflection point. And that inflection point indicates the steepest portion of the slope here. Well, the steepest portion of the slope, I'm going to put a dash mark right there, is going to end up being the greatest magnitude of velocity. So I'm going to draw that all the way down here. I'm going to put a big dot right there. That biggest dot corresponds to the steepest positive slope up here. This slope back here is definitely less steep than back here. That means the magnitude of velocity is less. This slope here is less than this slope here. That means the magnitude of velocity is less. And I can do the same thing on the other side. In the extension phase, I can look for periods where there's increasing negative slope and then periods where the slopes are starting to decrease. So we're looking at changes or where the inflection from changing from increasing to decreasing slopes is happening. I'm going to put that about there. It's a sketch. It's not perfect. That's going to be the maximum extension velocity, and I'm going to put a big dot down here. All right, so once again, I've got a starting point for velocity, no velocity. I've got a maximum flexion velocity. I go back to 0 velocity. I hold 0. I go to maximum extension velocity, and then back to 0. And like I introduced these little dots here, I can do the same thing. This slope right here is definitely less steep than this slope back here, even as badly as I drew that. And the slope here is less steep. That means the magnitude of velocity is going to be less steep. So now I'm going to draw this, the shape of the angular velocity curve. And again, sketching, trying to be true to what's happening. I'm going to draw sort of that same type of S-shaped curve. All right. And then I'm going to draw that here, down here, that same type of curvature. Oh, that was terrible. That's an error. And then on the extension side, I'm going to do the same thing. I'm going to try to pass through there, pass through there. Well, it's sketching. I'm not a great artist. But get by. Okay. So now I have all of these are positive velocities. All of these are negative velocities. These are all flexion velocities. These are all extension velocities. But now I have some periods where they're speeding up through flexion, slowing down through flexion, speeding up through extension, slowing down through extension. This is exactly the same as our speedometer exercise that we went through. We have a direction of movement and we have a magnitude of velocity. This is going to be, let me see where I'll write this. You're going to get the notes. I will write speeding up through flexion in this region, okay? Anywhere in here. This region is going to be slowing down through flexion. So we're still going through flexion, but we're slowing down, okay, in this region. In this region, speeding up. And same thing here, we have speeding up through extension, and then we have slowing down through extension. All right, and I'll divide that here between that max. So I'm speeding up through extension, I'm slowing down through extension. I'm speeding up through flexion, I'm slowing down through flexion. I'm zero velocity here, zero velocity here. All right, so now we've got our velocity profile. I'm speeding up through flexion, I'm slowing down through flexion. I'm speeding up through extension, I'm slowing down through extension. The same information about velocity is in this plot. It's just easier to see when we actually calculate velocity and then plot it. Same thing, speeding up, slowing down, speeding up, slowing down. So now let's do angular acceleration. And our formula for angular acceleration is how fast angular velocity is changing. Well, just like up here, this is rise over run. Well, now if we look at this plot, the rise is delta omega and the run is delta t. So our slope is exactly angular acceleration. So our slope with the velocity versus time plot yields acceleration, angular acceleration. So now we're going to do the same thing. I'm going to draw down these discrete points here as best I can, drop it down to that plot. I'm going to go ahead and drop this one down now too. And this one would line up with that inflection point up here. I'll drop this one down, this one down, this one down, and this one down. All right, now level one, what we want to do is identify the direction of the acceleration vector from the velocity versus time plot. So notice I don't need the position plot now. I can leave that off the screen at this point. And all we do is look at the direction of the slopes, and that tells us the direction of the acceleration vector. Anywhere in this region, any splice of data I take and calculate a slope, all those slopes are going to be positive. That tells me my acceleration is positive. Angular acceleration is positive. Anywhere in here, we've got negative slopes. That tells me angular acceleration is negative. Anywhere in here, I've got negative slopes. That's angular acceleration vector has a negative direction. Anywhere in here, this positive slope, positive angular acceleration. And where there's no slope, no change in angular velocity, doesn't matter what the time period is, angular acceleration is going to be zero. No slope, no angular acceleration. And that's going to be in the middle where we paused and in the beginning and the ending phases. So what's great about this graphing is I would like you to be able to identify where angular acceleration is either positive or negative. Remember, angular acceleration does not tell us the direction of rotation. Here's a negative angular acceleration, and we're going through flexion. We're going through flexion. Here's a negative angular acceleration, and we're going through extension. We're speeding up through extension. We're going through extension as our position plot shows. This is all still extension. This is all still flexion. Nothing's changed, okay? So now, I'll draw the acceleration plot in just a bit, but I don't want to worry too much about the magnitude of acceleration here. If we can zero in and pick up on where angular acceleration is positive or negative, that's a huge victory. And to recognize that the direction of the angular acceleration vector does not tell us direction of rotation, Because again, here's a positive angular acceleration, and we're in the flexion phase. Here's a positive angular acceleration, and we're going through an extension phase. All right. What this tells us is the slope of the angular velocity versus time plot is positive. It's positive in this region, it's positive in this region, but they have different meanings. I'm speeding up through flexion, I'm slowing down through extension. So to really interpret this plot, we really need our angular acceleration plot. This plot is really, really critical. In fact, a lot of times when I ask you about angular acceleration, I don't want you thinking about angular acceleration. I want you thinking about angular velocity, how it's changing. All right, so really try to work yourself back up to this plot, because I think this is the plot that's easier to see and understand. So now let me draw in the angular acceleration data. If I did my math and I calculated this, it would look something like this. Okay. All right. The magnitudes, they're off a little bit, but the pattern would be what this is. I have periods of positive angular acceleration, indicating that I am having speeding up through flexion. I have periods of negative acceleration. I'm slowing down through flexion. I have periods of negative acceleration, speeding up through extension. And I have positive acceleration, slowing down through extension. Now my magnitudes of acceleration are changing, but don't get caught into trying to interpreting changes in the angular acceleration. That's another plot that would take us down to create another graph. We're not going to do that. Right now, we're going to just recognize that if I'm at this point, and that's a positive angular acceleration, versus if I'm at this point, which is also a positive angular acceleration, and both of these points are in the same phase, they're both indicating speeding up through flexion. All that's happening here is we're speeding up through flexion faster here than here. Here we're just speeding up a little bit. Here we're speeding up a lot. Here we're also speeding up through flexion. Less than the fastest, a little bit more than this point, but it's still speeding up through flexion. All right, so on a test, I would likely label these points ABC, and I'd give you some other points, and I'd ask you which of the following points indicates slowing down through extension. Given these data, if I give you the answers or the possible answers on on the acceleration plot, what I strongly recommend you do is, okay, the question is about what am I speeding up or slowing down through extension. Don't look at this plot, look at this plot. So which point falls in the phase that indicates speeding up through extension? Is that what I said? Speeding up through extension, it would be F. If I said which of these points was slowing down through extension, I'd have to say G. Why? Because G occurs in this phase. If I said which of the following points would be speeding up through flexion, well, don't look at this plot, look at this plot, find that speeding up through flexion, and then it would have to be A, B, or C. Okay, so hopefully that helps when you start trying to think about test questions, as well as trying to understand the relationships. But this is sort of neat to have this model, even though we have instruments to calculate or measure this information. It's good to be able to sketch these out to have a sense of what the data will look like, even before we turn an instrument on. Okay, so that's angular position, velocity, and acceleration from a graphical perspective. All right, thanks everyone.